Good morning and welcome to the session 5 of 6 of the Water Bootcamp. My name is Laura Ramos and I'll be the MC for the session. The bootcamp covered hydrology, where your water comes from, surface water rights, and groundwater yesterday and earlier this morning. They were recorded and will be available for your viewing via the World Ag Expo show portal until February 28th. During this session, we will cover CV salts, followed by the blueprint for water in the San Joaquin Valley. The bootcamp is brought to you by the California Water Institute at Fresno State, which mission is to engage San Joaquin Valley, California, and the world with Fresno State faculty, staff, and students in the pursuit of a sustainable water resource management solution through outreach, research, and education. CWI wants to give a special thanks to World Ag Expo for allowing us to present this information. We wish we were with you in person in Tulare this morning and hope that we're able to join you next year. Questions will be taken at the end of the session, but please feel free to add them to the chat function on Zoom or on the World Ag Expo show portal as we go. The session speaker is Carl Longley, Professor Emeritus at Fresno State. Carl?
Hello, I'm Carl Longley. I'm a professor emeritus here at Fresno State and also a member of the Central Valley Regional Water Quality Control Board. And it's my pleasure to be with you today to discuss a topic which is near and dear to my heart, Central Valley Salinity Management Program. This is a world problem, and as you can see from the map that's showing, we find issues in countries, many countries throughout the world. Certainly our focus is on the United States, but we will be discussing problems elsewhere just to show the magnitude and some lessons learned as we've gone down the road. 77 million acres some years ago is the amount estimated. That's about, that's hectares. That's about 200 million acres. And that's a heck of a lot of land. As we look at the salinity control program here at Fresno State, as we look at the salinity program through California, we find that for the Central Valley, it's a basin-wide problem. We have long-term sustainability goals, which are focusing on maintaining good water quality. And secondly, while improving the poor water quality that we now have because of the huge amount of salt that we've picked up particularly in our groundwaters. This program, because of the problems that we have with salinity, and we'll be looking at the monetary impacts of those, have resulted in the formation of the Central Valley Salinity Alternatives for Long-Term Sustainability Program. It's a program of the water boards of California. And that's abbreviated, and you may be more familiar with it as CV salts. Our management goals, of course, are to slow down degradation while we focus on improving practices that can effectively control the salinization of our soils and water supplies. And the things that we do want to do is certainly to protect our high quality waters, and that fits within our anti-degradation plan. But we also are focusing on meeting long-term water quality objectives, and where we find that it can be carried out to carry on long-term restoration. The first management goal is obviously to protect safe drinking water supply. And for that, we have devised both short and long-term solutions. The problem here, primarily at this point in time, is from nitrate. And the short-term solutions are, of course, providing drinking water to those folks who do not have safe drinking water. That's primarily the disadvantaged communities within our valley. And The long-term goal, of course, is to be able to provide safe drinking water at the tap rather than providing it at a kiosk or by delivering bottled water. A second management goal is to balance both salt and nitrate loadings. There is some interesting work going on this to be able to accomplish this. And then lastly, something I'll discuss in more detail is implement managed aquifer restoration. This is more than just improving the water quality. The water quality of that aquifer is extremely important. If contaminated with nitrates, it impacts public health. Salt significantly impacts crops and our ability to use that water. But we can also do managed recharge, and that gets at the problem that we have of not having enough groundwater. The impacts of groundwater that have resulted in significant subsidence are wide throughout this valley. That has to be addressed also. So there's multiple goals, and there's interacting goals with other programs that we have through this effort. Where we talk about objectives, we have to have something to measure it against, and these are our measures of success. Certainly, as I mentioned, nitrate is a major problem, and we're looking at mechanisms to better provide alternative water supplies. We have to have a operational plan, if you will, to legally authorize discharges from modern farming practices and to manage those discharges so that they do not provide environmental impact. And we're working, of course, to save the good waters that we have and working on ways to restore degraded groundwater. I should point out here that if you have a lot of nitrate in the groundwater that you're using for irrigation, that nitrate is a nutrient, an important nutrient for plant life, and it should be considered within your irrigation, within your fertilization plan as an essential nutrient. Lastly, an approach that recognizes the diversity of conditions across the Central Valley is extremely important. In as short a distance as less than a mile, you can find significant differences in soil quality. Other factors that influence how we operate, whether it be the greater use of surface water or greater use of groundwater and so on, the types of crops grown, and we can go on, but there's tremendous diversity of conditions across the Central Valley that we have to recognize in the planning that we do. Where do these salts come from? And you can look at the practices as well as I do, certainly from human contribution, wastewater treatment plants, septic tanks, the kind of things we do to produce economic goods, whether it be food processing, manufacturing, or the produced water from oil production in the southern part of the valley, dairy and feedlot wastewater and irrigation water and runoff all add to the kind of salt sources that we consider. Now, delivered delta water, water that is coming out of the water projects, add significant salt, actually add a tremendous amount of salt. It so happens that the pumps are at the southern end of the delta, and we have tides daily that shove salt up into the lower part of the delta, which is captured and picked up. Some of that's captured and picked up by the pumps and is exported southward. So, excuse me. One of the things that would happen with the tunnel project, it would greatly improve the quality of water that we're receiving in the southern half of the valley, into the San Joaquin Valley, it would significantly decrease a lot of the salt load to the San Joaquin Valley. The impacts of the salt, and I'm going here to Australia, to the Murray-Darling Basin to discuss this. This is effects of a drought, the so-called big drought in Australia in the Murray-Darling Basin. I might point out the Murray-Darling Basin is a big ag area in Australia. But between 2001 and 2009, it was a 12-year drought, but the worst part of it was 2001 and 2009. There were significant expressions of salt. You can see it in urban, dryland, and irrigated areas. But it was a problem that really affected their production, their ability to grow crops, their ability to use the water for other beneficial purposes. On the your left, you can see in Iraq the example where the white soil. That's salt, which is trapped in the upper layers of the soil. And this is the same area, I might point out, where the famous gardens of Babylon flourished during biblical times. This over the centuries has been a very, very productive agriculture area, but a large amount of it being taken out of production by salt. The right photo shows a evaporation pond for processing agricultural drainage water. We at one time had a large number of these in the Central Valley, a lot of salt there. We're not using them nearly as much as we did. The large pond is still found on the Tulare Lake Drainage District, where they are using evaporation ponds for drainage water. They have a minor amount of selenium, but they have to carry out mitigation measures for that selenium. Elsewhere in the valley, where we had larger concentrations of selenium in our drainage water, it was concentrating and causing impacts on waterfowl. Malformed waterfowl are resulting from large consumptions by the waterfowl of selenium-laden waters. Selenium is a contaminant. It's also an essential element in your body, I might point out. It's one of the things you need in the enzyme system to protect you against cancer. Certainly, if you go to New Zealand, it's the lack of any selenium there has resulted in white muscle disease in the sheep. It's on the east side of the valley. We have to feed cattle selenium, but it's in the right amount. It's a necessity. When you get too much of it, it becomes a poison. It's an essential element out of place, really, on the western side of the Central Valley. When we talk about the Central Valley salt issues in economic terms, we can see that large amounts of salt in the soil really poisons the soil. Decreased production results with eventually the soil going out of production. If you don't remove that salt, one way to remove it is to flush it with higher quality water, pushing it down into the vadose zone. It eventually finds its way to the groundwater. So then it's part of the water that you're pumping. And that's the dilemma. You have to find ways to minimize the amount of that goes to the groundwater. Then secondly, the impact on drinking water supplies by selenium and nitrate is very significant. So the direct cost of this, and these are 2009 costs, is a direct annual cost of $1.5 billion with a statewide annual income impact of $3 billion. And that's folks losing jobs. Those jobs may be in farming sector, but they're also in food processing sector, in the transportation sector, and so forth. The kinds of sources of salt we have are diverse. You can see them there. Ag drainage, of course, the soil amendments that find their way into the groundwater include a lot of gypsum. A number that was given to me by DWR was that nominally we import about 800,000 pounds of, 800,000 tons of gypsum into this valley each year. That's part of the total salt load of 2 to 7 million tons of salt that are imported into this valley. Large part of it by the water supplies and the other sources that we showed below. Certainly from the Delta comes a lot, and that, as I mentioned earlier, would be addressed by the tunnel project. Most of this salt is unmanaged. Some programs such as real-time management, that's where we control when we dump salt into a surface water so that we have high flows that result in dilution of that salt and movement of that salt towards the marine environment. A small amount of it, deep well injection. The deep well injection, for the most part, has been unsuccessful. Examples are the city of El Paso, which was attempting to do deep well injection on their wastewater. And in fact, that wastewater ended up eventually sealing the wells. The other example would be a cheese manufacturer who was attempting to use deep well injection. Once again, plugging occurred. Where successful deep well injection has taken place is in the petroleum industry with the produced water, but they're typically putting that water back into the a similar aquifer from which they take it out. They are very, very careful with the chemistry. It is essential that they are, so that they don't seal up that rock with salt. And what happens is your pressures go up, so you can't continue to push any significant volume of water into the well. So these are problems that point to a viable solution to be able to address the salt problem. So we've gone through part of the development process, and this is a pyramid. Pyramid really doesn't judge time too well. This whole thing started off in 2006, and you go to the bottom part of the pyramid, that's where we started all of that work. And where you see the arrows going up into salt and nitrate control programs, that's where we are right now. We're looking for at least 35 years out to be able to really implement effectively salt and nitrate programs. Currently, we're in what we refer to as the prioritization and optimization studies as we figure out the best way to manage this salt from an economic standpoint, from a technical standpoint, from a public health standpoint. And then we will move into construction and implementation. I've mentioned the prioritization and optimization program. It has many parts to it. The first significant thing, if you look at the if you look at the blue boxes at the top, it talks about a conservative salinity permitting approach and an alternative salinity permitting approach. This pertains to the folks out there who are discharging salt. Who is that? Well, it may be municipalities, it may be individual farmers, it may be industry. It is all of them. So they have to make a decision of whether they are going to enter into the conservative or the alternative salinity permitting approach. The conservative is you go it alone, you do it yourself. You're responsible for the things you see up there. Source control, the board, Regional Water Quality Control Board would give you a permit. Conservative effluent limits should be expected. You have basically no use of assimilative capacity, time schedules, or and you're not eligible for exception and variance considerations. If you decide to go the other direction and join in the group effort, you band together with others in your management zone, and you share costs, you participate in development of management plans for that management zone. I talk about management zones. Management zones are part of the basin plans that have been adopted in 2018. They cover the major basins that we, or sub-basins, I should say, that we have. The ones with priority 1 are found in the San Joaquin Valley, and if you live in that area, you can expect a management zone coming your way, and you've probably already received letters about the need to be involved in this activity. Moving on, as we move into phase 2, you have a opportunity to reevaluate whether you want to go on your own or join with others. And at that point, we move into a permitting process. If you happen to be working with your folks in your management zone, you are continue to participate in setting control plan strategy through the various projects which are developed. And we find that this continues into phase 3, the project implementation. That's where we're into construction. And at the end of the construction, we are moving on with planned projects, operating those projects as we move ourselves onward into the total scheme of focusing on effective salt management. This gives a quick overview of what I've just been talking about. I've talked about most of these others, but I want to focus on the bottom right where it talks about conduct required monitoring. There will be required monitoring. If you're going it alone, you're responsible for your own monitoring. If you're with the larger group within the management zone, then that'll be programs that representative monitoring programs carried out by your group. Management strategies. There are a number of these to consider. I'm not going to be talking about these in any detail, except to say that when we talk about mature technologies on the upper left, those technologies need to be further developed. Right now, I'm involved in some work on reverse osmosis and ion exchange to make them more economical, to make them effective at reducing the salt load and the brine stream that's produced from treatment. There's a lot of other technologies that are being discussed in addition to the ones shown here. Brine disposal from treatment processes is particularly difficult in inland areas such as the San Joaquin Valley. Some areas in the United States, and a good example of this would be Utah, have a built-in place to put their brine, so to speak. They have the Great Salt Lake, but we don't have a Great Salt Lake. I guess we could create something like the Salton Sea that will probably be discussed as we proceed onward. We would have to find where it's going to be. But the focus currently is on finding ways to otherwise manage our salts. And one of these ways is transporting it out of the valley, whether that be by truck and rail or a Bay Area wastewater treatment plant or permitted Bay Area outfall. The discussions have been underway in the past with the East Bay Municipal Utility District of using their outfall. They have excess capacity. They have a permit, that wastewater discharge permit that would have to be amended. But certainly that is one direction. However, if you're transporting salt out of the valley, you're taking a lot of water with that salt. Even if you concentrate that salt up, you would like to reclaim as much of that water if you can reclaim it so it can be reused, it would have to be able to fit into the economics of the reuse of that water, but it would certainly be beneficial in the long term. Analyses that have taken place have shown that sustainability of agriculture and other economic activities in this valley can only be achieved if salt is exported out of the Central Valley. Is that a true statement? Certainly, that is central to all evaluated salt management alternatives. However, if you're going to consider this, you have to consider obviously the costs that are involved. And you can see the costs, these are about 2 years old, these costs. The costs for the capital cost is on the order of about $7.5 billion, $7.7 billion. And the annual O&M costs are slightly less than $800 million a year. You ought to realize that out of this, you're getting a product water with an estimated value of $909 million per year. So the O&M cost may be well worth it. The capital costs become a major consideration. That's going to have to be paid by somebody, and that obviously becomes an issue of pretty intense discussion. Another way of showing these costs is shown here. There are alternatives. If we do not go to marine disposal of our brine stream, the salt out of this valley, what are those alternatives? First of all, as part of the solution, we have to consider managed aquifer recharge. It's very important. We've overpumped. We have a lot of aquifer space that we can put water into. We need to capture excess waters, particularly in the springtime, when those waters are flowing in our surface streams and rivers, and we have to put those back into the ground. We need the ability in this valley to, particularly in flood years, to be able to move a lot of water very quickly and put it into the ground. That has its pros and cons, but it has a very big pro, and that it begins to address providing more water for this valley, and at the same time addressing the issue of the issue that we have for brine disposal. So it really comes down to brine disposal. Does it have to be a money sink on the red side of the ledger? And if we consider recycling, in other words, removing salts, finding beneficial uses for those salts, we may in fact develop an economic opportunity and save a heck of a lot of water that can be reused in the process. This means that we have to consider treating our salty waters, but we do have a market for the products that we can produce that has to be an early consideration. Products that can be produced or recovered, if you will, are acids and bases and salts such as gypsum and sodium bicarbonate. We use a lot of this in the valley. Nutrients, I've listed some of those nutrients. We have arsenic and selenium. We don't mine this in the United States, but these are contaminants of problems in our area. We have a challenge that we have to change the law. These are RCRA metals. They are now have to go to a waste site, but if we can economically put them into the supply stream, that also is a big factor in our economy, in that it's in the national interest to so do and not bring them in from other countries, especially China. And a lot of other products are available to be considered from the salts and other materials that are in this water. Some parting thoughts is providing a water supply, particularly in the areas of limited water usability, that is both of the quality that we need to support our economic activities, and at the same time we can do that in an economic manner so you can make a profit using that water. We have to do water recharge where high quality water is available, particularly during the flood season. And certainly agriculture drain and tailwater can be an important resource if we can effectively work those salts to be salts that have a higher value. Obviously, as part of this, we should be looking at salt tolerant plants that may provide important benefits. I want to thank you very much for your time. I hope this has been of some value to you, and I wish you a great day. Thank you.
Thank you, Carl, for that information. At this time, we'll take your questions. Thank you for joining us for this session. We hope it was informative. The session was recorded and will be available on the World Ag Expo platform until February 28th. We hope you're able to join us for the last session of the World Ag Expo Water Bootcamp coming up shortly. Thank you.